The topic for this video is the quantum mechanical model. The essential questions are: how do wavelength, frequency, and energy relate to each other? And how can we find wavelength, frequency, or energy when given the other two? So this is a picture of a light wave, and we're going to talk about the different components of waves. The first is the wavelength, and it's written with that kind of funny Greek letter that's called a lambda. And so the wavelength is just the distance of one complete cycle, so the distance from crest to crest you can see on the diagram there. And because this is a distance, we're going to use our units of length, meters. A lot of time though, the waves we're talking about are very small, so we'll talk about centimeters, or even if they're really small, nanometers. Frequency is another component of waves, and we just use an F to represent that in an equation. And that's the number of wave cycles produced each second. So if you pick a point and you count how many waves pass that point every second, that would be the frequency. The units are hertz, or 1 per second. Okay, so as the wavelength decreases, so as you look from left to right, the wavelength is decreasing, the frequency increases, and it's also sometimes written with a V. I know it's kind of confusing, but you need to be able to recognize that it's F or V. That's going to be increasing. Okay, and so if that frequency increases, it is higher energy waves. Okay, so it's higher energy on the right of this diagram than it would be on the left. Alright, so this is our equation to relate our wavelength and our frequency. And c is the speed of light, which is a constant. Okay, so it's always 3 times 10 to the 8th meters per second. So that's what you will always plug in for C. And then you will be given either the wavelength or the frequency, and you'll have to find the other one. Okay, so these are inversely proportional. So if your wavelength goes up, the frequency has to go down, and the opposite is also true. Okay, our other equation we'll be dealing with is energy equals H, which is Planck's constant, and times frequency. So as the frequency increases, the energy will also increase. And Planck's constant is always the same number. It's this 6.63 times 10 to the negative 34th joules times seconds. So if we're asked to calculate the frequency and the energy of a photon of yellow light having a wavelength of 575 nanometers. Okay, so first we're going to calculate the wavelength, and we can do that using our equation that has the speed of light in it. And I can just change this around. If I divide both sides by wavelength, it's going to cancel on the right, leaving me just with frequency, which is what I want to find. And so I'm going to do the speed of light divided by that wavelength. Now, the wavelength in this equation has to be in meters. So I'm just going to divide it, because I know for every 1 meter there's 1 times 10 to the 9th nanometers. So I'm just going to divide 575 divided by 1 times 10 to the 9th. And that gives me 5.75 times 10 to the negative 7th meters, which is what the unit has to be for this equation. And the nanometers cancel. So when I plug this in, I have 3 times 10 to the 8th meters per second over 5.75 times 10 to the negative 7th. And that was that C over wavelength. Okay, so then I just have to plug this in my calculator, and I will solve it, and I get 5.22 times 10 to the 14th over 1 second, which is one of the units for frequency. It also could be equal to that number of hertz. And those meters cancel out. Okay, so then it also asked me to find the energy. So now I have the frequency, I can get the energy. I always know H is 6.63 times 10 to the negative 34th. I just found on the last slide my frequency, which is 5.22 times 10 to the 14th. And all I have to do is multiply those two in my calculator to get my energy, which is 3.46 times 10 to the negative 19th joules, and that will be our unit for energy. And that's because seconds cancel out. Okay, so we're going to do another practice. It says calculate the wavelength in meters of radio waves having a frequency of 2.5 times 10 to the 6th seconds to the negative 1. So I'm looking for wavelength. I have C equals wavelength times frequency. So I can divide both sides by frequency to get it to cancel over here, and then wavelength is left by itself, which is what I want to find. So I'm going to take the speed of light divided by frequency. So speed of light is 3 times 10 to the 8th. We know that's a constant. My frequency was given to me in the problem. It's 2.5 times 10 to the 6th. I'm going to go ahead and work that in my calculator, and that gives me 120 meters. Okay, and that's because my seconds cancel. We're going to do another one. Calculate the energy of a wave that has a frequency of 4.2 times 10 to the third seconds to the negative 1. Okay, so I know my equation, E equals h times f. I don't know my energy. H is always the same, 6.63 times 10 to the negative 34th. And frequency is given to me in the problem, 4.2 times 10 to the third. So I multiply those together, my seconds will cancel, and I'll end up with joules. And my energy is 2.8 times 10 to the negative 30.